Welcome to Introduction to Automation. This is our first Zoom session, and it is our session where we introduce a lot of key concepts that we're going to be learning about in this course. And I've already introduced to you the book. I've shown you where to find it in D2L, and you will have an assignment to read through pages 1 through 32 over the next week. The purpose of the book is to provide us a pretty good methodology for doing robotic cell design. So I like the book, and I urge you to read it, and there will be a quiz. So let's talk about what the purpose of this presentation is. Number one, this presentation is the beginning of a journey. It is a journey to identify and justify automated system opportunities. In this presentation, I'm going to introduce those concepts. I will not expect you to become an expert at using them yet, but I want to introduce them. And then later on, we will start to dive into some of the more specific tools to calculate what value you can get if you automate something. We're also going to introduce the concepts of value stream maps, which is part of lean methodology. And we'll be diving further into lean methodology and how many manufacturing facilities use that and what value they get from it. In many cases, any kind of major automation project is going to be measured based on the concepts of lean. There are so many manufacturing plants right now that use this, it's almost become the standard. I've already introduced the book Lean Robotics to you. We will be diving a little bit into some of that book. We'll be talking about some of the tools that they offer in the book, and we're going to introduce you how they work. I'm also going to talk about some of the specific deliverables, the process and deliverables associated with lean robotic work cells as part of that book. So those are my purpose. So table of contents. The first thing we're going to do is talk about an approach to automation. I think automation is very much about mindset. I think that it's easy to get into the wrong mindset. So we'll talk about that. Number two, we're going to talk a little bit about how you target the right kind of automation opportunities. Number three, we're going to talk about, in general, what are you looking to define when you define a work cell? You can't really jump into the requirements right away. But what I want to do is introduce these requirements as different things you need to think about as you specify a work cell. And then once we've done that, then we're going to go in through the design process. First, we're going to talk about the traditional design process. We're going to talk a little bit about why that doesn't work. And then we're going to dive into the lean robotics design approach, which includes a manual task map and a robotic task map. Now, these terms, task map, it's not a great term. It's a little bit vague, but that's the one that the book uses, so that's the one we're going to use. A task map, think of it as a way of laying out how a particular work cell does stuff. So we call it a task map. And it does more than list tasks. It lists tasks plus a bunch of other things. So the book calls it a task map, and so will we. So the first thing we're going to do is get into approach to automation. And well, this is my approach to automation. It's not necessarily shared by all engineers. You will see a lot of overlap, though, with everybody's approach. The first thing I like to start with is steal ideas shamelessly. The best innovations have already been innovated somewhere else. Chances are, if you see a successful implementation somewhere, it's already gone through a lot of steps to vet it out. And if you have the same process in your plant and you could steal their design ideas, that is something I would encourage highly. They've already justified it. They've already worked out a lot of the issues. If you can take that idea and apply it to your plant, it's usually going to be a pretty good win for you. The next thing approach is I want you to find success stories with a long-term, clear ROI, that's return on investment. In other words, when you steal your ideas, pick stories that aren't just, they just didn't just implement, right? A lot of people crow about their robot system they just installed, and it looks great. They've got videos, they have a little, newspaper reporter come in and take pictures, and they put them in the local paper. But you don't really know how well it's been operating until it's been operating a few years. And after it's been operating a few years, then you talk to the engineers and the operators, and you find out just how good that system's been. So find a success story that has a long-term history, a long-term, not super long-term, but enough to know it's operating properly. Another approach to automation, and probably the single most important factor when it comes to really getting the okay to implement something, is identifying and convincing stakeholders. Stakeholder means a person who has some sort of investment in that particular facility, someone who really cares about it. And I don't just mean financial investor. Stakeholder might be the plant manager, might be the operations manager in charge of that plant. It might be the CFO of that company. Or other stakeholders might be the senior operator in charge of that process. He might be or she might be a stakeholder. Other stakeholders might be the vendors, which are supplying critical parts for you. They maybe not have a big say, but they may affect your process. So you have to convince the stakeholders. Usually it's the plant manager, CFO, CEO kind of people, but sometimes it's a broader range. Sometimes it's operators. Because let me tell you something straight, operators, if they're a senior operator, been in charge of a process a long time, they have been known to make sure automation projects were unsuccessful. And I have some more stories to that effect, which I'm not going to dive into in this presentation. Next item, develop a plan to get critical mass in automation skills and projects. Critical mass means I've got not just one robot of each type, and then each robot has its own programming language, and each robot needs its own training and spare parts. No, you don't want that. You want to develop a critical mass. Find a process that can be duplicated out almost identically so that you have the same robot 8 times. That way you only have to have one robot programming language that everyone needs to know, one set of spare parts, and one kind of training. And so all this will help you develop the value in your plant. Having a single robotic cell with a single robot usually isn't where you're going to start. You're making your big payback on an implementation. Think about a critical mass. Think about implementations that will gather speed and spread across multiple parts of the plant. The second to last one on this list is build a culture of automation. It's hard for you to do that as a technician, as an engineer. This is something, though, that you would work with your plant manager on. A plant manager needs to build a culture of automation where employees are rewarded to work with automated systems. They don't feel punished by automated systems, and that everything is a matter of optimizing what you do. If a plant manager wants to go to an environment where automation just replaces everybody, you're not going to be building a culture of automation. In fact, everyone's going to push back on automation. So you have to find a way of getting the things that really need to be automated, and not try to have a culture of, I'll call it robot oppression. And the last one kind of goes back to the critical mass. You have to build a knowledge base. As you come up with these projects, you have to store the information. If the vendor is supplying you this robot, you have to make sure that the design information, the programming information, configuration information, all of that information is stored in a place that's not going to go away. Targeting automation opportunities. So here we're going to talk about how you find places in your facility to automate. I know a lot of you already work in plants that you're pretty highly automated. There's probably not a lot left. Some of you work in places where there's not really a lot of chances to get the work cells that we're talking about here. But some of you are. And I'm going to encourage you to target your opportunities this way. Number one, safety. Safety is always where you start. If somebody is at risk doing something, then using a robot for the activity will reduce that risk. It's probably the first and best way to support an implementation. For instance, we have cases of robots lifting pallets of powdered material or blocks that could put off dust. And so the previous operators were doing that by hand. They're hurting their backs, they're breathing the dust. So that's an ideal operation for a robot. They could pick up these heavy things that operators had trouble with. And these aren't high value activities from a business standpoint, but they can be extremely high cost to the personnel. So by putting a robot in there, you avoid that back problem, you avoid the risk of inhaling powders that may give you long-term lung problems, and you really have a much better chance of being successful as a business. So we always look for safety issues and injury-prone areas. I think that's the same thing. The next area is new production. Anytime you're putting a new production line in a plant, you want to consider automation. There's always a temptation to just grab whatever kind of you're doing with the old production line and duplicate it. But this is often a case where if you need to hire new employees and you need to train them and you need to bring them from the ground up, then this may be a place where the cost of doing all that hiring and training and supporting those new employees is going to exceed the cost of an initial implementation of a robotic system. So by putting the robot in from the beginning, you really might find you're highly justified. Same again. So obviously, if you have an existing Workcell, you might want to repeat it. High manual handling, large volume, low skill threshold. So these are all key areas to look at. If you have a lot of parts running through a facility, a lot of times automated systems are going to run at a higher speed. So you can put more parts through. You can run at a higher volume. And if you're not really applying a high skill to that labor, it's very simple assembly, for instance, you might find that the robot can do it a lot more efficiently. So you can get a better quality product at a higher speed with different kind of robot systems. So these are the areas you're looking for: manual handling, large volume, low skill. And then last but not least, and I don't really like this term, we could consider lights out operations. Lights out is a term that some managers use to describe a fully automated factory or area within a factory, where you can turn the lights out because there's no people in there, normally speaking. It's only robots, it's only automation. I don't like that concept because it's so hard to achieve and it's such resistance from your operators and your personnel. I think the lights out concept causes more problems than it's worth. However, there are exceptions to that. If it's a dangerous facility, like a nuclear facility where you've got radioactive components and you really don't want any operators in there at all, that's an area where you can have a lights out model. You can have the robot running alone. So these are all areas that you should consider for targeting automation. The one that's probably most important for all of these is safety, injury prone, and high manual handling with large volume and low skill. So let's talk a little bit about justification. We've talked about it on the edge, but specifically when we talk about return on investments, what we want to do is look at the total cost of implementation, right? And then look at the total benefits of that implementation. So when we talk about project justification, we talk about converting an existing operation to something else. And there's usually some savings and there's some costs. So the savings are sometimes what we call cost avoidance, like health and safety costs. If we look at our long-term expenditures, say you're working around a hot vat of liquid right? And every once in a while, somebody takes their rubber glove and plunges it into the vat to go grab a part that fell in there without thinking too carefully about it. And liquid gets in around their glove. They pull that sucker out filled with burning hot liquid, and now they've got a major injury. And this actually happened in one of my plants. And it's a common area for safety costs. So you can calculate that. There are calculators out there for health and safety costs based on risk assessments, and you could develop a cost for potential injury. We also can look at quality problems if we have existing quality problems because people make mistakes. We could look at personnel, like their salaries, benefits, training, and downtime due to personnel. If someone calls out unexpectedly, then a lot of times a plant might have a small area down unless they can hustle and get somebody new in. And if that occurs, then you simply can't make product, and there's a cost associated with not making product. Training as well is a big issue. All of these are associated with personnel. Most robotic systems include at least some personnel savings. Another area of savings is increased volume, increased cycle time. So I can make more product. I can improve quality and I can make more product. And this is probably the reason why the most successful robotic and automated work cells are successful, is because they can go faster, 2, 3, 4 times faster, run all the shifts than a human could. So costs are something else. That's the other side of the equation. You've got your benefits, your savings, and now you've got your costs. And just to example, I mean, obviously you have your initial robot, plus all the wiring, plus the installation, plus all that sort of stuff, the initial system in total. Usually you can amortize that over 5 years. If it's a big system, it might be 10 years. But in addition to those costs, we have some costs that some managers don't really talk about. If you're going to have a robotic system, any kind of automated system, you're going to have ongoing supervision and operators that are going to have to support that system. You can't just walk away from it. You have to feed it, you have to check it, you have to unload it. All these things need to occur. So you do have ongoing supervision and some operator support. You obviously have an increased maintenance cost. Let me say that again. You have an increased maintenance cost. That's because guys like us are expensive. We know how robots operate. We've been trained to program them. We've been trained to program PLCs and do the wiring, and we are not cheap, and we're worth every penny. But the fact is that if you're talking about a manual operation, you don't need highly skilled maintenance support. When you're talking about an automated operation, you do. And we're a little bit more expensive. And you have to budget some reprogramming and some tweaking and tuning on any system, as well as ongoing specialized training for any components in that work cell that are not part of your business so far. Now, in the justification area, the new construction is sometimes a little bit trickier to justify because there isn't a current state, a current cost. New construction has the ability to do this implementation from scratch. So we don't have any existing process to deal with. So we usually have a slightly different approach. We want to look at the different options for implementation, where we do hard automation, where we build a custom machine that makes this part that does what that work cell could do. A custom machine, that hard automation, is usually for extremely high volume, but very low flexibility, cases where I don't want to change my product much, and I probably won't ever change anything. We could create a robotic cell where we have some sort of volume, medium to high volume, but we also want to have the flexibility to change the product up. I might have 5 or 6 different kind of products I can run through that cell, and I have the ability in-house to reprogram that robot, change out the fixtures, and have that cell do something completely different. Hard automation, a custom machine, will not be able to be that flexible. We could do a manual cell. A manual cell is lower volume, medium to low volume, with maximum flexibility, but you build in all of the costs of personnel, and you build in all the problems of quality, etc. So manual cell is what you would compare to if you had very low volume and you wanted the most flexibility. Or you could outsource it. Outsourcing is sometimes the best approach. I say maximum flexibility, but it really depends on who you outsource it to. But outsourcing also has an extremely high cost, not just the cost of the individual part, but a cost of change. Because if you want to change up something and how you make that part, and your outsource for that part has a change control process that's very expensive, then that change may never occur, may be very, very difficult for you to occur. So you need to pick the low cost option based on the kind of parts, the variety you have, and the volumes that to be produced. Also, you might have unique safety requirements. You might also have, I call it core industry requirements, or core requirements associated with mil spec that you have to deal with. Each business is a little bit different. So you have to look at the safety, accuracy, quality, industry requirements for the parts that you're making. And any choice selected based on having the cost to produce fit within the end product margin calculations. In other words, you have to look at to make sure whichever one you picked, the overall cost per product fit in the initial plan to make sure your parts are cheap enough. Otherwise, you won't find any way to implement it all. So at this point, let's go review a couple of different let's take a look at a couple of videos here. I think what I'm going to do is pause the recording, show you the videos, and then we'll restart the recording. All right. Okay, so now we're going to talk about the traditional design process. And this is the one the book talks about. And it's also one that I've experienced as well. It's a traditional, what they call waterfall approach for design, where you go through a process where each step of the project, has a particular set of requirements, and it takes you through to an end full implementation. So a traditional design process is one where you very much do a relationship chart between the different devices, and you create a from and to chart. So you're going to go from a manual operation or no operation and to a fully automated operation. So you create a relationship diagram. You lay out everything in a space. Basically, you figure out what each space requirements are, and then you lay it out in a space diagram. And that whole thing is part of a big layout process. And it's an iterative process. It takes forever, because after you figure out a layout, then you ship it down to your plant manager, and he looks at it and says, oh, it doesn't work for me. I hate it. Move it around over here. And then when he's done with it, you pass it on to your operators, and they're like, that can't possibly work. This is over here, and this is over here. It's no way it's going to work. So you get that feedback, you go back to your manager, and then you fix it, and then you realize that you've totally screwed up the layout possibility for where that robot's going to sit. So it takes a long time, is my point. So traditionally, we've got a space diagram. We alternate layouts are evaluated, and that takes forever, until finally, in the end, you do the layout selection and installation. This is just the layout. It doesn't include all the other criteria for integration, for power wiring, for air and hydraulics, and everything else you might need. This is just the traditional layout design process. And so I think the book provided this chart to me. This is kind of how they do traditional implementation, where you do a study. That is, you watch your operators run for a while and you figure out what the picking and placing and moving is. And then you create a task relation and flow diagram, right? You lay out a whole flow diagram. You lay out your space, you come up with the alternate layouts, and then you create an optimal layout based on that flow diagram. So that's kind of the traditional approach. It still works, don't get me wrong, but it takes a long time. And even after you come out with your optimal layout, stuff changes and you find yourself having to go back and redo. What I find is that to optimize your machines, you really want to create a balance between the efficiency and speed of the process, the cost of the process, and the flexibility. So going through this long, iterative, traditional approach doesn't take into account of being able to tune these things, right? It really creates more static systems that are designed to work a certain way together and just hammer through those steps as efficiently as possible. But what if I want to change things? What if I want to make it more flexible, right? The traditional approach maximizes the current requirement set, which might be speed and efficiency. It also maximizes costs because you're really just focusing on requirements, and it minimizes flexibility. But flexibility is important for any kind of automated system. I want to be able to have the flexibility to run different kinds of parts in the future that I may not be thinking about right now. And I want to have the flexibility to tweak and tune that automated system. If I'm just going to build a hard system that's only designed to run one way, then why am I using a robot? Robots are kind of expensive tools if you're going to turn them into hard automation. So instead, what I really want to do is focus on using the robots for things that might change. So now we're going to talk about the lean robotics design approach. We've talked about the old approach a little bit. We've talked about the lack of balance between the ability to be flexible versus the cost and speed. Now we're going to talk about the lean robotics approach. And the lean robotics approach is pretty much a traditional design approach in some ways. In the old days, I used to look at a process, a business process, and I would say, all right, the current state is this. We call that the as is. That's the current state. And then we want a future state, and we call that the to be. So we had the as is and to be, and that was our way of looking at business processes and manufacturing processes and thinking about what we had to do to make them run more efficiently, the as is to be. Well, in the lean robotics world, we have something called the manual task map. The manual task map is a documentation of the current state. Manual implies that it's got a person doing it. Now, in most facilities, it's not usually completely manual. In most facilities, there is some automation involved, but this book uses the term manual task map, so we're going to stick to that. Now, a task map includes a lot of things. These 7 things on this list here. We identify who the customer is. In other words, who is the end person who's going to put value on the product coming out of that Workcell. It doesn't mean the customer that you sold a sales order to. It might mean the next step downstream in that manufacturing process. So the customer is really the person who's going to grab that product next in your facility, whether it be a shipping department and then go to an actual customer, or it's going to go to a next Workcell and have more work done on the part. So we want to identify the cell customer or customers. We also want to identify the valuable output. In other words, what is the output on the cell and what is the value of that output? And next, we define the input. So we go back to the beginning of the process. We talk about the input. We also describe the process. These are your tasks portion of your task map. So the process is broken down into bullets, which are your different steps that your robot cell, your automated work cell is going to do. And then we talk about information, because in any modern world, we do have information associated with that manufacturing process. Information might be sales order information. How many parts are we going to make on this batch? It might be specifications. What are the width and thickness and height and depth of the part that we're making? It might have quality specifications. I might have smoothness criteria. I might have tolerance criteria for a width or a depth. I might have color. I might have any number of criteria that could be information that needs to flow somewhere as part of this Workcell. The next area is what I call KPIs. And this is an important term. It stands for Key Performance Indicators. And it is a measure, a metric of how that cell is operating. Key performance indicators. Now, most cells have at least one metric, which is production rate, parts per minute or parts per hour. That's usually the classic cell key performance indicator. But I might have other ones as well, like quality, like flexible changeover rates. I might have other things as well. So I might have multiple key performance indicators associated with that cell. And the key thing about making these implementations is you have to follow through, and the key performance indicators are often part of your justification. So you have to follow through and make sure your cells really operate according to specifications. And then finally, you need something for the manager to read. So we create a summary. You create a little summary map, a one-page view of all these 6 documents. And that summary map is what you show your managers. And that helps you explain things to them. So this is an example of a summary map from the book, a manual task map summary map. So you start with the manual task map. This is the current state. And so the first thing you do is describe who the customer is for the manual process, which probably won't change in the automated process. You're going to talk about the output for the manual process. That probably won't change either. However, instead of throwing parts in a bin, I might need to put parts in a rack. I might need to store these parts in different volumes than what I did originally in the manual way. But this task map is the manual task map, and you will describe in detail what that output looks like. Input, the same thing. We've got our input number 3. Is it going to be a bin full of parts loose on the table, or is it going to be a rack? For the manual task map, we will describe exactly how it is now. Then we also need to uncover secret squirrel aspects of those inputs. What if I've got an operator who is wiping those parts down and he puts them back into that rack or onto that tray completely wiped down? And if you didn't have an operator there, you wouldn't get those parts wiped down. So we need to make sure we document that. So if we need to have a cleaner in there for the parts before they go into that work cell, we need to now add that as part of our input. The cell process itself, that's in the middle, number 4, and that's the steps that the cell is producing. Now below that, I show a little chart, this little chart right here, value added time. Every process step, we need to have a record of how much time it takes. And this little chart shows seconds. Seconds might be appropriate for most manufacturing processes, but sometimes it might be minutes or even hours, but seconds is probably usually appropriate. And we also have non-value added time. So in total, we've got a total time that a part or a batch of parts takes through that cell process. This is where we record that. That timing is very important because it will be our first and most important KPI or metric as we start changing the process to a robotic one. And speaking of metrics, we can see number 6 here on the right. This is where we document all of our metrics. That might not, throughput rate might not be the only one. We might have other ones. And then last, we've got 5 information flow there in the middle. Any information that's going into the cell and coming back out of the cell. So here's an example of a manual task map summary. It shows you your inputs. It gives you a few key bullets about that inputs. 4 types of parts, aluminum blocks stacked on table. Obviously, this is okay for a summary, but you really want to document all those parts and what their dimensions are. And we need to know what those aluminum blocks look like, what their conditions are, and we probably need to know how they're being stacked currently. The process itself, you can see a bunch of bullet points in there, and then they give you the summary of how much value added time versus non-value added time at the bottom. And they show you information flow very generically. They just show you operators talking to each other and pressing buttons on the CNC. So there's not a lot of information flow shown in this diagram. KPIs, there's exactly 2. One of them is a quality, first pass yield 97%, so it's 97% yield, which is pretty good for quality, I guess, but not great. And the rate, which is 210 parts per day. The output is on a tray, and the end customer is an operator who can bring tray of parts to inspection station every 2 hours. So that specifies how often those trays are collected currently. So this is an example of a summary only task map. If you want all the details, then you go through 1 through 6 and look at those pages where somebody's hopefully documented all the details. Another important deliverable early on is you have to look at the manual cell layout. We talked about the task map, but here we're talking about the actual dimensions of the layout. And this is a very typical machine operator layout where you've got a table, stainless steel table, usually set up in front of a machine. In this case, it's a CNC machine. The operator is going to stand between the table and the machine, grab parts off the table, load them in the machine, use an Allen key to tighten the fixture, fire up the machine, machine runs, pop the machine open, blow off the part, loosen the fixture, put the finished part onto a tray. And the output would be to the inspection station next, where the parts would be inspected. So this is an example of a layout. It's very important in these layouts to make sure you have all the dimensions, which I don't see in this, which I want to see overall dimensions. I want to see how much space that machine is taking up, how much space I have around that table, how much space between the table and the aisle where forklifts might be going down there. I want to see the overall dimensions, and I want to understand how that current layout works physically. So I only see some of those dimensions, but I see that there appears to be a door that's 1/2 meter wide, and I've got a depth in the machine, so the operator is going to reach into the machine 0.4 meters. So that's useful. It tells me what kind of range I need on my robot to reach in there. So, oops, I jumped further. So let's talk about the lean robotics design approach in terms of the robotics task map. So we did the manual task map, but now we're going to dive into the robotics task map. And we follow the same steps. I'm not going to repeat that. And we have the same summary map, exactly the same in terms of layout. But now, instead of filling it with content from the operator standpoint, from the current manual standpoint, now we're going to fill it with a robotic Workcell standpoint. And it could be that the task map won't change very much. The robotic task map example wouldn't change very much, but the layout will definitely change. So here's an example of a robotic layout. Got the robot, you got a CNC machine, and now you've got a table of parts sitting there near the robot. I'm not sure why they put the controller between the table and the robot, but that's what they did. And then you've got a range for the robot to pick up parts from the in and drop the parts in a different tray on the out. They're missing some key things as far as I'm concerned. I would want to see a safety perimeter in here. I'd want to see overall dimensions. I want to see where the operator station would be. So they're missing some key stuff in this little example, but It's better than a kick in the teeth.